Differential equations have applications in electricity, specifically in the context of electrical circuits known as RLC circuits. This acronym stands for resistance R, inductance L, and capacitance C. So in this type of circuit, which is considered a closed circuit, and it has a standard diagram that is of this type here. Okay, so there are a few things to note. There is a part of this diagram where there is something that's called impressed voltage, is a battery or a generator. And then in both sides of this generator, there is one side where there is something that's considered positive, another side where it's considered negative. So you may have a mental picture of how batteries look like and how this positive and negative is well denoted in a given battery. So there is also a section here denoted as a switch with a dash line, and then there are parts of this circuit where we have the resistor, the induction coil. Here's the resistor, the induction coil on the top, and then on the right hand side we have the capacitor. Okay, so the idea would be to consider this closed circuit in a way in which differences in electrical potential are gonna cause electrical current to flow in this setup. So the electrical potential is going to be denoted here as E. Yes, I'll rewrite it again. E as a function of time t. Okay, this is going to be considered the electrical potential, and the battery is going to create a difference of electrical potential between the two terminals, between the positive terminal of the battery and the negative terminal. So we're going to consider E to be the potential to be positive if the potential at the positive terminal exceeds the potential at the negative terminal. And we will consider E to be negative if the potential at the positive terminal of the battery is less than the potential at the negative terminal. And also, we consider this potential to be equal to 0 if there is a match, if the potential in both terminals is the same. So this quantity E of t is also known as the impressed voltage. So everything here, that what we want to think of this system, what we want to think of it is a system that is changing with time. So in the independent variable is little t, time t, and at any given time t, we're going to consider that the same current, this is electrical current, flows in all points of the circuit. Okay, so the current is going to be denoted as I. This would be I as a function of time, and this is what we're going to consider the electrical current flowing at all points of this closed circuit. And then the idea of the flow is that there will be a sense of direction flowing from the positive. Okay, current is going to flow from positive to negative. Okay, and this would be from the positive terminal of the battery. This current is gonna, if you can follow here my the trace of what I'm indicating, this current is flowing. So let me do that again. So from the positive terminal of the battery, the current will be flowing, okay, on this with this sense of direction towards the negative. So the flow is assumed to go from positive to negative around the circuit. Okay, and so therefore these arrows here pointing, you can see the direction of these arrows almost on some circles. So you may think of this as having that clockwise orientation, and that clockwise orientation will be considered a positive flow. Now, in the case in which there is a reversed flow, we would consider a current to be negative. Okay, so maybe let me make a note of this. I was saying here the current flows from positive to negative. If this is the case, then we would have that I of t is positive, okay? And if we have that I of t is considered negative, then the flow would go, this is the negative sign, an arrow, into the positive sign. So the flow would go into the reverse orientation. So for a positive flow of current, we would have a clockwise orientation, something that looks like a cycle there, almost like a circle with arrows pointing, kind of how it is in this diagram. And you could have counterclockwise, right? Something that's pointing on the reverse direction, right? That would be considered a negative flow. When the current is 0, then for I of t equal to 0 at a time t, then there is no flow of current in the electrical circuit. Okay, so another thing to point out is that differences in the potential E of t, differences on this potential are going to occur at 3 specific points on the circuit. And these points are going to be called the resistor. Okay, so this is this point here, the resistor, and there is the induction coil. So that would be another point that is denoted here on the top. And let's say there is one more here that looks like an open space and kind of gate or something, and that's called the capacitor. So at the resistor, the induction coil, and the capacitor, each of them, resistor is associated with resistance, therefore here denoted with a constant with the letter R. Induction coil is associated with inductance, here denoted with the letter L, and the capacitor is related to capacitance. Okay, so each of these points in the circuit in which differences in potential will take place, each of these points has a positive and a negative component. Okay, so this will bring a notion of something, a term that's traditionally referred as the voltage drop. In the voltage drop across the resistor, the induction coil, and the capacitor is defined to be the potential on the positive side of the component, the potential on the positive side minus the potential on the negative side. So it's the difference between the potential at the positive end minus the potential at the negative side of the resistor, the induction coil, and the capacitor. Now, this notion or this definition of voltage drop, unfortunately, it's sometimes misleading because it's just tradition to call that, to use the word drop there. It doesn't necessarily imply that there is a decrease or that something is diminishing, okay? It simply refers to this difference between the positive side and the negative side of each of those points in the circuit. Now, the voltage drop across the resistor, let's talk about each of those points in the circuit. And so let's introduce here the voltage drop at the resistor, denoted here as V sub R. This is going to be a multiple of the current. And so we're going to use a constant R multiplied by the current, I of t, okay? And so that quantity R times I denotes the voltage drop at the resistor. And so R is assumed here to be a positive constant, it's a positive real number. And so now the voltage drop on the induction coil, okay, is going to be denoted here as the voltage it's going to be denoted as V sub I. Maybe V sub I would not be the best of notation here, but let's just assume that's the notation. So that's going to denote the voltage drop at the induction coil. This is going to be a multiple, not a multiple of the current, but rather a multiple, here denoted with the constant, the positive constant L, a multiple of the rate of change of current. In other words, we can write something like L times the derivative of I with respect to time. So here we're assuming that L is a positive constant called the inductance. Okay. And the previous quantity V sub R, the positive constant R, I must say, is called the resistor. And then the voltage drop at the capacitor, here we're gonna need to denote. Okay, let's make a note here. So at the capacitor, we're gonna need to define electrical charge. So the charge is gonna be denoted with the state variable as a state variable Q, and the definition is that this Q of t is given by Q sub 0 plus integral from 0 to t of the current. So I'm going to use an integration variable here, little s ds. Okay, so this is the definition of electrical charge that is stored at the capacitor. And with this definition, you can see easily that when we differentiate Q, the rate of change of the charge is precisely equal to the current. But very importantly, we're going to use this positive constant C called the capacitance to denote that the voltage drop V sub C, okay, the voltage drop at the capacitor is given by 1 over that constant C times the charge. So we have defined the voltage drop V sub R at the resistor, the voltage drop V sub I at the induction coil, and the voltage drop V sub C at the capacitor. We have defined these three quantities. So one thing to keep in mind is that on these type of formulations, it's very important that we have clear what are the units, okay? And so this is very briefly mentioned here that you have to keep in mind that some of the units involved include amperes, ohms, henries, coulombs, farads, and there is a way of there are conversion constants, and so that you can convert from one unit to the other unit. And just to establish a few things on the quantities we have introduced, the impressed voltage is denoted as E of t, that has units of volts. The current, electrical current I of t, has units of amperes. Charge is denoted with Q of t. So E of t, I of t, Q of t, they're all functions of time. The charge has units of coulomb. And then remember, R, L, and C are constants. Resistance has units of ohms. Inductance has units of henries. And capacitance has units of farads. Now, one of the things that we are going to do is that we're going to make an analogy between the electrical circuit and mechanical vibrations. And so here we can actually go back to where we have the circuit, and we can make a note about the following. Okay, so there's something called Kirchhoff's law. Kirchhoff's the law of Kirchhoff. Okay? And this law establishes that the sum of the voltage drops in a closed circuit of this type, which is called RLC, is equal to the impressed voltage. So this law says that V sub R plus V sub I plus V sub C is going to be equal to, so the idea of this being a closed circuit, it having some flow of current, is that this battery or generator, right, or generator is bringing or is injecting this voltage, and there is a sense of this in flowing across the system. So there is a match between this potential E of t and the voltage drops on each of these points. Okay, so the addition of the voltage drops will match the impressed voltage. And so if we write these expressions for what we, so maybe you can write this here below. So V sub R equals R times I, and V sub I, we have L times I prime, and V sub C we have here as Q over C, and this would be equal to E of t. Okay, so we could rewrite this as a first order. There is a derivative that we can write here, L I prime plus R I plus 1 over C Q equal to E of t. So that looks like a first order differential equation. However, remember, we're assuming that here, so first this is a first order. This is a first order ODE. The way this is proposed here, the I of t and Q of t are the state variables, or they are the unknowns, right? State variables or unknowns. So the way this is currently proposed there, we have a differential equation is first order, but there are two unknowns. So we can do something to actually rewrite this differential equation. So let me switch gears here for a moment. So let's remember that since the definition of charge is Q sub 0 plus integral from 0 to t of is ds, we can differentiate in both sides of this expression. Let me write this again. So Q of t equals Q0 integral 0 to t I of s ds, and we take the derivative with respect to t in both sides of this equation. So this Q of 0 is a constant, so that's going to be equal to 0, and then this right hand side here, using the fundamental theorem of calculus, this would become I of t. So we have that the derivative of Q of t with respect to t is equal to I of t. The rate of change of charge is equal to the current, which also implies that the differentiating again, the second derivative of Q is equal to the first derivative, or the second derivative of the charge equals to the rate of change, instantaneous rate of change of current. Okay? So we can then rewrite this law of electromagnetism is common. So we can rewrite Kirchhoff's law Okay, meaning that we had L times the first derivative of I plus R times I plus 1 over C Q equals to E of t. And the problem with that first order differential equation was that I and Q were unknowns, but using, I'm going to call this here number 1 and number 2. Using number 1 and number 2, we can substitute in the first term L times the derivative, the first derivative of I, that can be substituted with 2. And also on the last term here, 1 over C times Q could be substituted by, the middle term R times I can be substituted using the expression 1, where I is equal to the first derivative of Q. So using 1 and 2, we obtain let me write this as it was, L times first derivative of I, which would be the second derivative of Q, plus R times I, but I, according to expression 1, is the first derivative of Q. And then we have 1 over C times Q and the impressed voltage, E of t. So we have rewritten the law of Kirchhoff as this expression that's now entirely, the advantage is now this differential equation is second order. It's a second order ordinary differential equation, and it has one state variable or one unknown. And that state variable is the charge, Q. Okay? Now, very importantly, this differential equation, the second order differential equation, has coefficients L, which is a constant, R, which is also a constant, and 1 over C, which is also a constant.